Okay, so we can start, I guess. Now it is already 5 minutes past 6, so we can start. So, am I audible to everybody?
Yes, sir.
Thanks. Uh, so, so, good evening, everyone. I am Abhik Deb, and I welcome all of you to the second week live session of the course Concepts of Thermodynamics, which is being offered by Professors Dr. Suman Chakravarti and Dr. Aditya Bandyopadhyay. Um, I shall be dealing with the live sessions, wherein we will be discussing some of the assignment problems to clear some of the doubts that you might be having with the concepts that are taught in the class. So you can it will be more of an interactive session. So I request all of you to be present every Friday from 6 to 7 p.m. to make this program a success. Uh, and regarding the interaction, you can ask me the questions related to the problems that we'll be solving by unmuting yourself, or you can type in the chat box, or you can post your queries in the discussion forum as well. Uh, so we can just begin with it. Let me just check if uh, one is waiting. And as the screen, as the meeting screen won't be visible to me, so if somebody joins in between, so just let me know so that I can admit that person. Thank you. And so is this screen visible to all? Oh, sorry, I have not shared it, I guess. So is the screen visible to all now?
Yes, sir.
Okay, and I am audible, right?
Yeah, yeah.
Okay, so let us begin with the first problem. So a piston of mass 5 kg is fitted in a cylinder of cross-sectional area 5 cm square. This piston cylinder assembly contains 1 kilogram of saturated water vapor at equilibrium. If the water vapor is now heated at a constant pressure to occupy thrice its initial volume, then the final temperature of water is, we have to find that the final temperature, what will be the final temperature. So you can see, so this is a piston cylinder arrangement, and it contains 1 kg of saturated vapor. That means there is no liquid, only vapor is present, and the piston, which is having a mass of 5 kg and an area of 5 centimeter square, is on this is exerting its weight on this um, saturated vapor. So if after this, if the system is, it is heated at a constant pressure, so that this, the initial volume what it was occupying, now it occupies thrice the volume, then what will be the final temperature of water? So first let us start with the free body diagram of the piston. So you see, so this vapor, the vapor will be exerting a pressure upward on the piston, right? So this we are considering that the pressure that it is applying on the piston is P vapor, and due to this pressure, the force that it is being exerted is this pressure multiplied by the area. Now this, there is an atmospheric pressure of 100 kPa, so this atmospheric pressure will also exert a force on this, which is atmospheric pressure multiplied by the area, and the weight of this piston will actually act downward. So under the balance of these forces, we can find initially what is the pressure of the vapor, of the saturated vapor, that it is exerting on the piston. So if we consider a balance of the forces, then we can write that P vapor multiplied by area is equal to P atmosphere multiplied by area plus mg. So this P vapor, this will be equal to P atmosphere plus this mg by the area A. So the atmospheric pressure is given as 100 kPa. This is in Pascal now. So, and what is the mass? Mass is 5. We are taking the g, that is the acceleration due to gravity, to be 10 here for an ease of calculation, and the area is 5 centimeter square, that is 5 into 10 to the power minus 4. This is in meter square now. So the unit here becomes Pascal as well, and this is also in Pascal. So this comes out equal to, this is 100 into 10 to the power 3, and this is also, you see, this will be 10 into 10 to the power 4 here. If we take this in the so if this we take it up, it will become 10 to the power 4, so it will ultimately become 100 into 10 to the power 3. So the net pressure inside will be actually 200, this is 200 kPa. So yeah, so corresponding, see, in this only saturated vapor is present, right? So there is no liquid. So the vapor inside, the pressure inside, that is the pressure inside the piston cylinder, which is being exerted on the piston, is actually solely due to the saturated vapor that is inside. So we can say that in this condition, the since only saturated vapor is present, so we can say that this saturation pressure at this condition will be equal to the vapor pressure that we have found from there, the pressure of the vapor, and that becomes equal to 200 kPa. Now corresponding to this 200 to this saturation pressure, from the steam table we can find out what is the specific volume of the gas. Since this is only vapor, so the specific volume of the gas will only come. So corresponding to P saturation equals to 200 kPa, the specific volume of the gas, it will actually equate, this will become, from the, if we consider the steam table, from that corresponding to this saturation pressure, I am directly writing the value here, so it will be equal to 0.88568, and this is actually, since only vapor is present, so this will be equal to the specific volume of the entire mixture. So in the stage 1, the specific volume of the mixture will also be equal to this one. Now see, this is a closed system, the piston cylinder assembly is a closed system. So for a closed system, what happens if the mass is constant? Since the mass is constant, since mass is constant, Therefore, see, specific volume is what? Specific volume is volume by mass. So this portion, this mass, it is constant, right? So in the question it is given that the water vapor is now heated at a constant pressure to occupy thrice its initial volume. So since the volume, this value, it is becoming thrice. So that implies that this value, it will also become thrice, right? Since this is the volume is becoming thrice and the mass is constant, so this will also become thrice. So we can say that in the stage 2 the specific volume is equal to 3 times the specific volume in the stage 1, that is 3 multiplied by 0.88568, that becomes equal to 2.65704. Now we have to find the final temperature of water at this stage in this case. So corresponding to this, see, this condition corresponding the saturation, it was already in a saturated vapor stage. Now it is being further heated at a constant pressure, so it will come to a superheated vapor region. In the superheated vapor region, corresponding to this vapor pressure, we have to find the temperature, that is what temperature actually corresponds to this specific volume of the water vapor. So from the steam table here, this is a section of the steam table that I have shown here. You can see that it lies between these two states, okay. So between 2.61 and 2.66. So if we from the superheated vapor table, we have to find the T2 as so since there is no direct value, we have to do interpolation as usual. So the interpolation will be T2, that will be equal to 880 minus 860. These are the temperature differences. Now we have to consider the ratio of the specific volumes, that is 2.65704 minus 2.6141, and we divide it by this ratio. The ratio of the, I mean the values corresponding to these two temperatures of the specific volumes, that is 2.6603 minus 2.6141, and this value comes out to be equal to 878.58 degrees Celsius, which is the option number B here. So the answer is option number B, 878.58 degrees Celsius. So is it clear to everybody, or if you have any doubt you can ask? You can just unmute yourself and let me know if there is a doubt.
Hello, sir.
Yes.
Uh, uh, some students are waiting to join.
Yeah, yeah. I is there anybody else? So yes, I think everybody now is listening. Mm, yeah, so please let me know if somebody else is waiting to join. So is there any doubt? So if there is no doubt, then we can move on to the next problem. Okay, so let us move on to the next problem then. Saturated water at 30 degrees Celsius is contained in a rigid steel tank of volume 0.2 meter cube. It is used in an experiment where it should pass through a critical point when the system is heated. The mass of water, that is liquid plus vapor, inside the tank is, we have to find the mass of the liquid plus vapor mixture in the tank. Now, what is the initial condition? The initial condition, that is at stage 1, the condition is 30 degrees Celsius and a volume of 0.2 meter cube. Now, since the container, as you can see, since the tank is rigid, so it will have the mass and the volume both will remain constant throughout the process, whatever process you carry out. Therefore, the specific volume, which is a ratio of volume by mass, will remain constant throughout. Now, it is being said that it will be it is used in an experiment such that it will pass through the critical point. So the critical point for a particular whatever a particular substance, it is always fixed. It is a particular value of temperature and pressure and specific volume. So as it is stated that it will pass through the critical point, so at the critical point we know that what is the critical specific volume. So the for the a mixture of water, I mean liquid water and vapor, the critical volume is let me see, the critical volume for water, that is liquid plus vapor, it is 0.00310056 meter cube per kg. So since the specific volume remains constant, so at the critical volume, at the critical point, if the specific volume equals this one, then we can very easily say that the specific volume at the stage 1 will also be this. Therefore, at stage 1, the specific volume will be equal to this critical volume of the this one, which is essentially the specific volume at the stage 2, is the critical volume is equal to the critical volume, and that becomes equal to 31056. Now, so we have to determine the mass at the stage 1. So you see that the volume is already given in the mixture. So what is the mass? See, the mass is just the volume divided by the specific volume. So therefore, the mass of water, this is in stage 1. Okay, this is liquid plus vapor. This is equal to the volume by the specific volume. That is 0.2, and we divide it by this value, and the mass comes out equals to 64.4 kg. So this is this value. There is a slight change in the value because the source from where I have taken this question, they probably might have used some other steam table. So this slight changes are attributed to the smaller change in the values of the steam tables that we take from different sources. So the answer will be the option number A. Four point four kg. So is it clear to everybody? Please do let me know.
Yes, sir.
Okay, no doubt, right?
Yes, sir.
Okay, so we will now move to the next problem. See, now a sealed rigid tank contains 1 kg of water liquid plus vapor at 200 degrees Celsius with a volume of 0.005 meter cube. So it is at 200 degrees Celsius and the volume is 0.005 meter cube. The tank is now slowly heated. What happens to the liquid level inside the tank? So there the three options are given, four options are given, that the liquid level remains same in the entire process, the liquid level will eventually drop to the bottom of the tank, the liquid level will eventually rise to the top of the tank, and it cannot be determined. So you see, again we will make use of the fact that it is a sealed rigid container. So since it is a sealed plus rigid container, this implies the specific volume is constant. Now you see, let us suppose that the mixture is initially at the stage 1. Okay, so it is having a temperature of 200 degrees Celsius and a volume of 0.005 meter cube. Now it is being slowly heated. Now there can be three instances. There can be actually two instances. See, if the point 1 it lies to the left of this critical point, the vertically downward, since the volume, the specific volume is constant while it is being heated, so it will essentially rise up a straight line which will be parallel to the pressure axis. So if it is on this side or to the left of the critical point, then what will happen? Then it will, this is the liquid region, as we all know, this is the liquid region and this is the vapor region. So any point on the left of this critical point will give a liquid state. At any point to the right of this will give a liquid state. So we have to determine, essentially determine what is the specific volume at the stage 1, and we have to compare it with the critical point specific volume to find out which portion, which region it will go to when it is being heated. So initially, what is the specific volume? In a stage before heating, say before heating, the specific volume is it contains, see, this is the volume and this is the mass, so it is directly we can divide it. So this is volume by mass and this is 0.005 by 1, that is 0.005 meter cube per kg. Now the critical specific volume, since it is heated, let us suppose that when heated it crosses this dome, whatever the liquid, the saturation side, it can, this point 2 can be on this side also and this point 1 can be this side also. So let us suppose that the point where it crosses this dome is 2. So since it is a since it is the specific, throughout this process the specific volume remains constant, so it will move along a straight line and the specific volume will essentially remain constant. So V2 will also become equal to V1 and this will be equal to 0.005 meter cube per kg. Now we can what is the critical volume? In the previous example we have also mentioned this. So the critical volume of the critical volume for water this is equal to 0.0031056. So we can say that this is since this value, the value, it is greater than this one, so we can say and the specific volume values, see, they increase on the right hand towards the right. So we can see that, we can say that the specific volume at the stage 2 is greater than the critical point value. So when it is heated and it crosses this dome, it will ultimately, this is the entire vapor region, right? So it will ultimately, the entire liquid, whatever there be it in the container, it will ultimately convert to vapor. So all liquid ultimately It's converted to vapor. So if the liquid is getting converted to vapor, then what happens? Then the liquid level will eventually drop to the bottom of the tank, because it cannot rise, it will ultimately become zero. So the option B is correct. Answer is option number B. That is, liquid drops to bottom of the tank. So is this clear to everybody? Any doubt?
Hello, sir.
Yes.
Sir, in this question, that 200 degrees centigrade temperature given
Hmm.
is the surplus data.
Sorry, I didn't get you. Can you please repeat?
Uh, Hello,
Yeah.
sir. In this question,
Hmm.
I understood the question.
Hmm.
Also, your answer it is also correct.
Hmm.
But that 200 degrees centigrade temperature is given.
Hmm.
So is that data is surplus data, sir? Because we have not used this.
Yeah, we have not used this because this is essentially stating that the temperature is at 200 degrees Celsius and it is essentially below the critical point temperature, but
Yeah.
this is not actually required to solve the problem. Yeah. Okay. So anything else? Any more doubt?
Sir, again one thing,
Hmm.
if the volume of the vapor is less than the critical point,
Hmm.
then point one it
Hmm.
will come on the left side.
Yes.
Okay.
Yeah.
So in that case,
Yeah, we
this
will come to that. We will come to
uh,
that. The
yeah.
next problem is actually related to that only. See, in this case, let me see. It is visible, right?
Okay, sir.
Hmm. So, regarding this, the part that you were asking, we will be solving in
Yes.
this one. So, see, in the previous problem, if the mass is now 2 kg of water mixture instead of 1 kg, what will be the specific volume? So all the concepts remain same here. So the final this we can write that the specific volume of 2 is equal to specific volume of 1, and that will be equal to 0.0025. Okay. So again the critical volume is same, 1056. So here we can say that the final the specific volume at the stage 2 will be less than the critical volume. So when you heat it further, the entire mixture will turn into liquid. This happens essentially because the pressure at this point, see, these are the pressure lines, right? It moves like this. So the pressure becomes so high that they turn into a stage of compressed liquid stage, in which the entire vapor at this level of high pressure will turn into liquid. Thus, because of this, so the mixture entire mixture will become liquid. Therefore, the liquid level in this case, it will eventually rise to the top of the tank. Therefore, liquid level rises to the top of the tank. This is option number C. So I hope that the question that you were asking, this answers the question.
Yes. Yes, sir.
Is it perfectly fine?
Yes, sir. Okay.
Okay, okay.
Uh,
So, okay, so we will be moving on to the next problem right now. See, okay, so these are a bit, these were the previous problems were a bit, conceptual kind. Now we will be moving more into the numerical kind of problem. So, same, similar kinds, but we are doing more and more problems so that the concept, different kinds of concepts can become clear. Now, see, a piston cylinder assembly which contains saturated water, liquid plus vapor at 75 degrees Celsius, that is the stage 1. Initially, the piston movement is arrested using a pin. These are the pins, and the piston movement is arrested. And the water is heated till 150 degrees Celsius, at which all the liquid just disappears. So, see, since the piston movement is arrested, does this imply? This implies that the piston cannot move outward. So, essentially in this process, whatever the volume inside will remain the same. Therefore, in this heating process till 150 degrees Celsius, it will be essentially a constant volume process. Okay, and after this, now the pin is removed. This is removed and the water is heated at a constant pressure till it reaches 300 degrees Celsius. So from this stage, it reaches 300 degrees Celsius, that is a stage 3. Now, since it states that in the stage 2, the liquid just disappears. That means it is in the, at the point 2, it will lie on the saturated vapor line, that is the vaporization curve. Otherwise, any point inside it will contain both liquid and vapor. So since there is no liquid, just no liquid, hence it will lie exactly on this point. So stay from stage 1, we take constant volume heating, we reach stage 2 where liquid just disappears, and then at a constant pressure heating we will reach stage 3, which is in the, this is essentially in the superheated vapor region. So see, from the steam table, I have not shown the steam table here, but you can follow any steam table to come to the same results. I will just write the values here. So at 75 degrees Celsius, the saturation pressure, what is the saturation pressure? And this will be the pressure at the stage 1, that is equal to 0.032575 MPa. And the specific volume of the liquid in this stage, that is 0.00102584, and the specific volume of the gas, that is 4.1289. These are just direct values. You can directly go to the steam table at 75 degrees Celsius and take in these values. So now you can say that since this is a constant pressure constant volume process, and essentially the mass will as usual remain same, so the specific volume in stage 1 and 2 will remain the same. So let us first start with the stage 2. Now stage 2 is on the saturated vapor line. So at 150 degrees Celsius, the saturation pressure, that will be the pressure at the stage 2, that is 0.47616 MPa. And in this case, since it is on the saturated vapor line, so the specific volume at the stage 2 will be equal to the specific volume corresponding to the vapor gas phase of 150 degrees Celsius. So that is specific volume at the stage 2 is equal to the specific volume of the gas corresponding to this 150 degrees Celsius, and that is equal to 0.39245. Again, for constant volume process, volume process in a closed system, what will happen? The specific volume will remain constant, therefore V2 is equal to V1. This implies this V1 value that is equal to 0.39245. So what can we write in this? Since see the stage this one, it is within the uh, dome, liquid vapor dome, so there is it will have a particular quality, that is it will have both liquid and the vapor. So we can write this value as 1 minus x1 vf1 plus x1 vg1 0.39245, and from here if we put the values of vf1 and vg1, we will find that x1 it comes out equal to 0.0948. Therefore we have to, here we have been asked to find the initial quality of the mixture. Therefore initial quality of the mixture is is 0.0948. So this is answer to part number A. Now is it clear to everybody till now? These are so if there is any issue you can just ask.
Hello, sir.
Yeah,
Quality of steam, yeah, mixture is 0.09 and 448.
yeah,
It is a very and less.
yeah, it can be very less. Then if it is
Means,
very less,
sir, means it is nearer to the liquid.
yeah, it is nearer to the liquid curve.
Yes, yes. Means it's very less and dry.
Yeah, 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 yeah. It is
Yeah.
very less dry. Yeah, you are correct. It is very near to this one, and so it will see. In this is just a pictorial
Yeah,
representation.
yeah,
Okay.
yes, sir. For
Huh.
the given any data, we
Yeah,
have calculated.
yeah, yeah, yeah.
Uh,
Exactly,
because
exactly.
if it is a zero, then it is a exactly liquid.
Yeah, yeah, yeah. Almost liquid. Yeah,
Yeah.
yeah,
Okay, okay. Thank you, sir.
yeah. So let us move to the second part of the this thing. We have been asked to find the final specific volume of the water vapor. Okay, so you can say that see for the final specific volume, you can say this is the stage 3. This stage 3 is essentially at a superheated vapor region. Okay, so and we know since 2 to 3 is a constant pressure process, so the pressure at the stage 3 will be equal to the pressure at stage 2, that is P3 will be equal to P2, that is equal to 0.47616 MPa. Now, uh, yes, is there any problem? Any doubt? Okay. So, and it is given that the stage 3 is at 300 degrees Celsius. So, from the steam table, we can say that at 300 degrees Celsius, see this we have to find the final specific volume of the water vapor corresponding to this pressure, this pressure. But this pressure is directly not available in the steam table. So, we have to do an interpolation. So, at 300 degrees Celsius, corresponding to sorry corresponding to 0.45 MPa, the specific volume, this will essentially be only one, there is no Vf and Vg. This is only Vg actually, that is the specific volume, it is completely vapor, it is in a superheated vapor region, so the entire thing is vapor. So we will denote it by V only. So that becomes equal to 0.58140, and corresponding to 0.5 MPa, the specific volume will be equal to 0.5 52261. So you see that the between these two pressure points this will lie. So by interpolation, if we do the interpolation, we can find the specific volume corresponding to the stage 3. That will come out equal to 0.58140 plus this values from the steam table. Wait, 140, the corresponding pressure values, we have to take this ratio. So if we just do the interpolation, this is just a calculation, it will come out to be equal to 5506. So this will be the answer to the, this is the final specific volume. Okay, so is it clear to everybody? Any doubt? Any doubt? Okay, if there is no doubt, then we can move on to the next problem. So a 20 kg piston in a cylinder, this is a piston cylinder arrangement with a diameter, the piston diameter is given as 200 millimeter, is loaded with a linear spring and the outside atmospheric pressure of 100 kilopascal. What is a linear spring? Can you tell me what is a linear spring, anybody? Anybody? Okay, so well, the just a minute. Okay, so what is a linear spring? A linear spring is one in which the force exerted by the spring will vary linearly with the compression or expansion of the spring. That is, it is a linear function. Okay, so as we move on with the problem, you can say like when the spring becomes compressed, it will exert a force, right? So this force will vary direct linearly with the value of the displacement of the spring. So it is stated that the spring exerts no force on the piston when it is at the bottom. So the relaxed portion of the spring is when the this piston is at the bottom. Okay, and for the state 1, this state 1 which is shown in the figure, it has a volume of 1 liters and a pressure of 300 kilopascal. Now the valve is opened in the stage after this, the valve is opened to let some air in from this supply and the piston then rises to 1 centimeter. So we have to determine what is the new pressure inside the cylinder. So let us start with the solution. Let us first draw a free body diagram of the piston. So there will be pressure from inside. We can write it as this is the force, this is the weight of the piston, this is the atmospheric pressure force, is the force due to atmospheric pressure, and in addition to these there will be the, since this is not the relaxed portion of the relaxed length of the spring. It is stated that the spring exerts no force on the piston when it is at the bottom. So when it is at the bottom, there will be no force, but when it is compressed, there will be a force from the spring on the piston. So due to this, let us suppose that this is the spring force, which we are assuming as Fs. Okay, that is Fs is the spring force. Now it is given that initial volume is equal to 1 liter, that is 10 to the power minus 3 meter cube. Diameter of the piston is given as 200. So diameter of piston, this is 200 millimeter. Okay, so we can see this volume is essentially what? This is volume is equal to the area of the piston multiplied by the this volume. This volume is essentially the area of this piston multiplied by this displacement. So to find this displacement, we can divide this volume by this area of the piston to find this what displacement has happened till the stage 1. So displacement of spring in this is in stage 1. Okay, so x1, this will be equal to this volume, that is volume by this area. So 10 to the power minus 3 divided by this area is 200 millimeter. This is essentially what, 0.2 meter. So 0.2 whole square, this comes out equals to 0.0318 meters or 3.18 centimeter. Now if we consider this free body diagram and do a force balance, then what can we say? From force balance, you can say these are the upward forces, right? Fs, atmospheric pressure force, and the weight of the piston, these are all acting downward. Sorry, they are all downward forces, that is they act downward. So the spring force, that is this one, it can essentially be written as so what is the inside pressure? See, the inside pressure, the pressure inside the cylinder in the stage 1 is given as 300 kilopascal and the atmospheric pressure is given as 100 kilopascal. So we can directly write it here, 300 minus 100, and we, since it is in kilopascal, so we'll multiply it with 10 to the power 3, and the area, that is pi by 4 into 0.2 square minus, this is the, so what is it? This is a 20 kg piston. So for 20 kg, this will be like 20 into 10. So if we do the calculation, it will come out to be equal to Newton, 6083.18 Newton. So is it clear till now? If yes, then we will move on to the next part. Can anybody just unmute and let me know if it is clear?
Sir, in the free body diagram,
Yes.
spring force will act in a downward direction.
Yes.
Is by the pressure of the fluid, pressure moves in the upward direction.
Yes.
So spring get compressed.
Yeah, see, this is the see, when the spring is in its natural length, then it is completely in a relaxed position. Now if you are trying to force it upward due to the pressure of the air, right?
Yes, sir.
So it, what will be the reaction of the spring? the force spring will try to push it downward, and hence the spring force will move downward, will act downward.
अच्छा
Okay.
अच्छा
If it had been in the opposite, like if it was pulling it, then it would have been extended. Then the natural tendency of the spring will be what? Then it will try to pull it back. So the spring force will in that case act upward.
So means sir, it is the opposite to the direction of the compression. It will enact.
Yeah, see, the spring, anybody, it will try to reach in its equilibrium position, right? In which
Yeah.
it was in its natural state, more you can say. So when it is compressed, it will for it to get back to its natural state. What will happen? It will have to force the piston downward, and
Yeah.
hence to resist this compression, it will insert a force in the downward direction.
Okay. Okay, sir. Thank you, sir.
Okay. So now we will move on to the next part. So as I initially stated that what is a linear spring? A linear spring is one in which the spring force it varies linearly with the displacement. So for a linear spring, this spring force, this is equal to K multiplied by X. You know this K, right? This is the spring constant. So as x increases, this will there will be this is a displacement of the spring. There is either compression or expansion of the spring, and there will be a linear variation of the spring force due to this. So from this we can find, we know this one, right? This is the x1 is the initial displacement of the spring till stage 1. So if we divide it, we will define the value of the spring constant. So this comes out equals to 191294.97 Newton per meter. Now in the stage 2, what happens? The air is let into this volume by this supply line. So naturally the spring will be further compressed, which is stated that the piston rises by 1 centimeter. So the spring is getting further compressed now. So what is the after air is let in, spring gets compressed by further 1 centimeter. Okay, therefore the final displacement of the spring, that is the compression of the spring, will be what? This is 3.18 plus 1, that is 4.18 centimeter, that is 0.0418 meters. So the new spring force will be what? Let us take it as 1. Okay, this was the stage 1. So the new spring force will be K multiplied by x2. That is, this spring constant will remain constant. This is a constant. So 191294.97 multiplied by this value. So the new spring force will come out to be equal to this one. See, the spring force has increased from around 6,000 to about 7,000, around 8,000. This is due to, as we are compressing the spring more and more, it will exert a higher value of the spring force to oppose it, and that is where, and this force is actually increasing linearly, and hence it is a linear spring. So now if we apply the force balance on the piston, force balance on the piston, we can say that similar, the forces will all act in the similar direction only, same direction only as before. So let's say Fs2 plus mg plus this atmospheric pressure multiplied by area will be this internal pressure in the stage 2 multiplied by area. So what is the pressure inside the cylinder in the stage 2? That will be equal to the atmospheric pressure plus the spring force and this one divided by the area. So the atmospheric pressure is 100 kilopascal and this spring force is what, 7996.12 plus what is the weight of the piston? Weight of the piston is 20 kg. So mass of the piston is 20 kg, so the weight will be 20 multiplied by 10 and the area will be pi by 4 multiplied by 0.2 square. So it comes out equals to, this is 100 10 to the power 3 plus 260.89 into 10 to the power 3. So the net pressure comes out to be equal to 360.89 kPa. Okay, so this is the option number A. So the new pressure inside the cylinder will be side cylinder is equal to 360.89 kPa. This is option number A. So is the solution clear to everybody?
Yes, sir.
Okay. Okay, so let us then move on to the next problem. So a 2-meter cube rigid tank having air at 150 kilopascal and ambient temperature at 300 Kelvin is connected by a valve to a piston cylinder assembly as shown in the figure. The piston of area 0.1 meter square requires 300 kilopascal below it to float. That means this is essentially given what? This piston to balance the weight of the piston and the atmospheric pressure so that it will start rising up is 300 kilopascal. If the pressure inside below the cylinder equates to 300 kilopascal, only then it will balance the weight and the atmospheric pressure to make it rise up. Okay, now the valve is closed and the piston is allowed to move up slowly, and the valve is opened and the piston is allowed to move up slowly, and then the valve is closed. During this process the air temperature will remain constant at 300 Kelvin. If the final pressure inside the tank is 120 kPa, then the height through which the piston has risen is, we have to determine the height through which the piston has risen. So what is essentially given here? This is a rigid tank. From here the air is allowed to move into this cylinder. Now after a final state of 120 kPa, we have in the tank we have to find out to what height this piston has risen in this cylinder. Okay, so what is the, let us start with the solution. So the initial conditions are the volume of the tank, it is 2 meter cube. This is a rigid tank again. Okay, this is a rigid tank. And the pressure, this is 150 kilopascal, and the temperature is 300 Kelvin. So considering, if we consider air at this pressure and temperature to be an ideal gas, then and if we apply this law, ideal gas equation essentially, then this is the mass of the air inside the cylinder at the initial stage before the valve is opened. So this implies that the mass of the cylinder, mass of the air inside the rigid tank, not the cylinder, the rigid tank, it will be at T1. So therefore what is the mass? This is a AP1 is 150 kilopascal and temperature is 300 Kelvin, and volume is 2 meter cube. So let me put the values. This is 150 into 10 to the power 3 multiplied by 2 divided by this is 300 Kelvin and this is R. So it will come out to be equal to 1000 by R, and we are keeping it that way for now. Now again, after the valve is opened, now the valve is opened and the air from this tank will now flow to the cylinder. We will consider two aspects now. First we will consider the tank after the valve is opened, and then we will consider the cylinder. So for first considering the tank, when the valve is opened, the air temperature remains constant at 300 Kelvin, but the pressure inside the tank drops to 120 kPa. Okay, so and the volume is essentially the same because it is a rigid tank. So after the valve is opened, the volume is the same, the temperature is also 300 kPa, sorry 300 Kelvin, but the pressure now has dropped to 120 kPa. Therefore, corresponding to this, the mass of the air, see under this condition, under these conditions, there will be a particular value for the mass that is remaining in the tank, because some mass has already flown out of the valve into the cylinder. So the mass that is remaining in the tank can be found out from the conditions in the stage 2. So the mass remaining in the tank, that can be given as P2V2 by RT2. So we will just put in the values. So this comes out equals to 800 by R. Sorry, there is an R. 800 by R. Okay. So initially the mass inside the tank is the same one, and after the valve is open, the mass remaining in the tank is M2. So what mass has left the tank? That will be the difference between these two masses. So therefore the mass of air that has left the tank, which is equal to, sorry, just a minute, which is equal to, let us say, delta M, that will be equal to M1 minus M2, that is is 200 by R. Okay. So this mass, the mass that has left the tank will essentially be the mass that has entered this cylinder through the valve. So we can say, therefore, this delta M mass of air moves into the cylinder. Therefore, let us say that this is the mass of the air inside the cylinder, that is delta M, and that becomes equals to 200 by R. Okay. Is it clear to everybody till now? Is it clear to everybody?
Yes, sir.
Okay. So let us move on to the next part now. Now what happens inside the cylinder? The mass inside the cylinder, the mass of air inside the cylinder we have determined as from the difference of the masses, and inside the cylinder the it is stated that the piston is moving up, and we have to determine the height. So since it is moving up, we can say that it has started to float, and the pressure required for it to float is 300 kPa, right? So since the pressure, since it is flowing, so we can consider that the pressure inside the cylinder has attained this value 300 kPa, and that is why only it is moving up. Okay, so the pressure inside the cylinder, that is 300 kPa, since piston has since piston is moving up. Now the mass of the cylinder we have mass of air inside the cylinder we have already determined. So what is the and the temperature? Now see, the temperature during the entire process, it is stated that the temperature of air remains constant at 300 Kelvin. So the temperature inside the cylinder will also remain the same. So the temperature of air inside the cylinder, that is also 300 Kelvin. So if we use the ideal gas equation again, we can determine what is the volume of the air inside the cylinder under these conditions. So this is what mass of the cylinder, that is 200 by R. 200 by R, we multiply it with R. This is the temperature is 300 and the pressure is 300 into 10 to the power 3. So that is why we didn't put the value of R, because it will ultimately get cancelled. So the volume comes out to volume of the air inside the cylinder comes out to be 0.2 meter cube. Okay, now the area of the piston. What is the area of the piston? The area of the piston is given as 0.1 meter square. Here it is 0.1 meter square. So area of piston, zero point 0.1 meter square. Now, so what is this essentially? Since now if the piston has risen to this level, this volume will be what? The area, this area, this volume, this will become equal to the area multiplied by the height through which it has risen. So if we divide the volume by the area of the piston, we can determine to which height the piston has risen. So therefore piston has risen by H equals to this volume of the cylinder by area of the piston, that is 0.2 by 0.1, that is 2 meter. So the height to which the piston has risen is given as is the height to which piston has risen is 2 meters. Okay, so is it clear to all?
Yes, sir.
Okay, so looks like we have reached the end of our time as well. So is there any doubt in the session that we did today?
Sir, I have just a small doubt.
Okay,
In question number 3,
okay, question number 3, right? Okay,
things are any clear.
okay,
In this question, suppose the volume of the mixture given
hmm,
it is equal to the critical volume.
okay, yeah,
And a V1 equal to the suppose critical volume.
yes,
Then this follow this path. It passes through the critical point.
yeah,
then in that case, what will be the liquid level will rise? Yeah, liquid level will drop. What should
See,
be the
then
answer?
in that case, it is what you can say. I mean, the critical point will be something like when it essentially the all the liquid ultimately changes to vapor,
Yes,
right?
sir. Yes, sir.
Okay. So if we consider it that way, then also till from the critical point onwards, from the .00 point onwards, that is a critical point onwards, if it is exactly equal to the critical point value, then from that also it will directly convert to vapor. Then also the liquid level will drop, because
Yeah,
ultimately if the specific volume is point exactly it is matching to this point, then also
yeah,
it will be what the entire liquid will convert to vapor.
vapor. If it is the converted into the vapor means liquid level will drop.
Yeah, if see the liquid level is converting to vapor, then what happens? The liquid in the container, it is decreasing, right? So if it
Yes,
is decreasing, then the liquid level will drop.
drop.
Okay, so that answer your question?
Okay, sir. Okay.
Okay,
It is clear now, sir.
okay. So I hope that the questions have been helpful for your understanding. So okay, thank you for attending today's session.
Uh,
You can leave.
no, thank you very much, sir. You have clear all our doubts.
Thank you.
Okay, thank
Okay,
you.
please join in the next session.
Okay, definitely, sir.
Okay, okay.